All right, so in thermodynamics, there's essentially every single system has a certain amount of what we call internal energy, which we symbolize with a capital E. By the way, capitalization matters a great deal in this chapter, so take extra care to be conscientious of it. And so, as the crash course video noted, we are usually interested in the change in energy. So delta E, change in energy. Delta always means change. Change is always defined as the final energy minus the initial energy, right? And so this delta actually could apply to anything. You could have a change in volume, which would be final volume minus initial volume, like we did for the titration experiment. Okay, so delta always means change, final minus initial. When you're talking about thermodynamic quantities, we have three different things that really matter a lot, and you have to pay attention to all of them. Otherwise, your answers are going to be saying, like effectively the opposite of what you meant. So the first thing is the magnitude of the measurement. So the number, right? The bigger the number, that has significance for you. All right. The unit matters, right? So if I have something that's measured in joules and I'm comparing it with something measured in calories, that's not apples to apples. I can't do that. It won't make any sense. I need to convert some stuff, which is why we learned dimensional analysis. Once again, to emphasize that, you need to be showing your work, all of your conversion work, using dimensional analysis to get full credit. And then lastly, in thermodynamics, we have the sign. Things are always either positive or negative, and we always include the sign, even if it's positive, because energy can be either one. And because of that, we need to encourage ourselves to get in the habit of having a positive sign or a negative sign. You should know that energy can also be equal to zero. We can have no change in energy for a system. That does happen. Where energy is zero depends on what you are measuring, and it is an arbitrary choice. There is nowhere in the universe that actually has zero energy, right? Which is why the sign is important, because we are arbitrarily deciding what zero is, which means some of our measurements will be positive and some of them will be negative, and we need to keep track of that. All right? Now let's think about this. If we have a delta E that is positive, all right, so our change in energy is positive, what would that mean about our system? So delta E final minus initial, if you end up with a positive change in energy, then energy had to go into the system. Because your final energy has to be bigger than your initial energy. So somewhere, the surroundings provided you with some extra energy. If you have a negative delta E, that means your system releases energy. Or you could say the system produced energy. That comes in handy later when you're writing chemical reactions that include energy in them, right? Because produced means it goes with the products. If energy goes into the system, it means the energy is a reactant. Okay, and so we can treat energy the same way we were treating matter in our chemical reactions before. Although good news is we don't have to balance it. We just measure it. All right? So essentially, keeping track of the magnitude of E, the unit of E, joules, calories, kilojoules, kilocalories, and the sign tells us everything we need to know about the thermodynamics of a system. I said capitalization matters, and here's why. In chemistry, and this is not universally true, all right? I think chemistry and physics do this. Biology isn't as diligent about it, and engineering has other conventions for state functions. But in chemistry and physics, when you see a capital letter for a variable, it means it's a state function. So a state function is something where it doesn't matter what happens in between. All that matters is the final and the initial state. The state function. So energy is a state function. And here's why, right? So if you're standing at the top of the Grand Canyon and you want to go down to the bottom, the total amount of energy is the same. You're changing potential energy into kinetic energy to do that. individual contributions to how that energy is dispersed will vary. So if you walk down to the bottom of the Grand Canyon, you personally expended more energy than if you rode a donkey down to the bottom, right? Or, you know, if you paraglide all the way down, you personally spent less energy to do that than to walk down, right? But here we get into the sticky situation where our system is not clearly defined. Are you the system? Or is the Grand Canyon the system, right? So it's important to understand that energy is a state function because of how we define our system versus our surroundings. The height overall is definitely a state function. You're starting at a certain altitude and you're going to get back down to a different altitude. And that is, it doesn't matter how you get there, right? The total amount of feet that you might have traveled might vary depending if you paraglide down. It's just vertical height, maybe a little horizontal height. Or if you walk down, you're going to spend obviously more distance trying to get downward. So distance does not count as a state function. Time, clearly different for each scenario, right? So that's not a state function, which is why time is abbreviated as a little t. Distance, little d. If you think about just how much energy you personally have expended, that would be different depending on which method you went about doing it. If you consider the total amount of energy, heat of the air molecules as you fly through the air, or the amount of energy the donkey has to expend, plus the amount you expend, if you add all of that together, the total change in energy will be the same for all of those scenarios. All right, and so that means energy is independent of the path, whereas distance and time are not independent of the path, so they are not state functions. But again, it's always easy to tell when something is a state function in chemistry because its variable is a capital letter. We've already seen some volume state function. So if, for example, I take a graduated cylinder and I fill it to 100, then I empty it, then I fill it again, then I empty it, then I fill it again, my overall change is still from 100 to 0. Okay? You can draw an energy diagram like this where your total, I can draw better than that, where your total energy is on the y-axis. The purple line represents our arbitrary placement of where energy is 0. And so initially our energy we have to put energy into the system and then we get energy back. And then we have to put a little bit more energy in and then we get a little bit more energy back. As it turns out, your delta E is only the final minus the initial, so that makes that a state function. It doesn't matter what happens in between because you got a partial refund, right? You got a little bit of a refund on the amount of energy that you got back here, and you get a little bit more back, right? So you got to add up your total expenses, your total costs, and that's the same as if you go final minus initial, all right? So energy is a state function. Let's look at a couple of those other variables. So we said earlier that the change in energy equals Q, which is heat, plus W, little w, which is work. Are those state functions? What do you think? Okay, so let's say we're starting at room temperature. We have to remove heat to get it into the ice stage, right? So minus Q to get it into ice. That's what your freezer does. It removes the heat from the stuff inside of it. If I want to boil the water, I have to add the heat. Okay? You don't get it back, right? So you have to put the heat in, and it's going to boil. So there's no refund there. There's no refund if you cool it either. It just goes away into the surroundings. So that makes Q not a state function. Similarly, work, which is usually what we call pressure volume work in chemistry. In other words, increasing pressure or changing the volume of something is how we do work. As it turns out, work is also not a state function because if I increase the pressure, then decrease and increase and then decrease, it still costs me work to do each one of those steps. all right? For those of you looking to become chemical engineers, whether you have to increase the pressure of a system or decrease it, it's both going to require pumps, okay? And that's going to cost you energy. It's going to cost you money. So while Q plus W is a state function, individually, heat and work are not state functions. It's like if I, as far as work goes, if I move my couch and then I put it back, I don't get that work back, right? It's gone, okay? So pressure, volume, work, the equation for work that we will use most frequently in chemistry is going to be negative pressure times the change in volume. And you'll notice pressure and volume are both state functions. But when you put them together, you get work, which is not. All right, so if we have a system with some zinc and HCl, and you guys did this in experiment 4, nothing's happening right now, but I have this system completely sealed, so I can watch what happens to our piston. Our piston is going to measure effectively the amount of work that can be done by the zinc HCl system. So we turn our container here to drop the zinc into the HCl. We see that bubbles are forming. So this will, of course, increase the pressure in this flask. That causes the piston to be pushed up. However much up it gets pushed is proportional to your work. So that's where your delta V comes in. Okay. So if we are making a piston effectively, so our pressure, the pressure at the end is going to be the same. It's around atmospheric pressure. We'll call that 1 atmosphere. The volume change is positive whatever this distance is. I don't know. There's no markings, I can't tell, but positive. So that means, since it's a negative equation, work, when it's negative, is done by the system. So you can imagine that somebody's going to have to push this piston back down to reset the experiment, right? That would be work done by the surroundings, which would be a positive W. Okay, so the signs are very important. They tell us where work is being done and by whom. Now, when we talk about reactions, not all reactions produce gas, but many, many, many reactions do produce quite a bit of energy. So we need a way to quantify that energy. We have this term called enthalpy. Enthalpy has the symbol delta H. All right? Basically, this is proportional to heat if the pressure is constant. So we will often say the heat of a reaction. We're referring to an enthalpy value there. Enthalpy is another state function, which means it's only the final and the initial that matter. If I take intermediate steps, they're not important. I don't have to know exactly what those are to be able to calculate our enthalpy of a reaction. This makes the math much more straightforward for us. Instead of doing calculus to find out the value of delta H, we can just do subtraction, literally final delta H minus initial delta H. We want to remember that final in a chemical reaction means products, and initial in a chemical reaction means reactants. So we can calculate the change in the enthalpy of a reaction just by knowing what our products and reactants are and looking at a reference table. This is called Hess's law, and you're going to prove it as part of a worksheet in class, probably during week 9.